So, some more properties of the stress tensor. First one, let's just keep in mind that now the stresses in the body, which is subjected to some forces, body forces, and some tractions, are not independent of these body tractions. They depend through this differential equation. This is the Cauchy's equation of motion. We'll talk about that. That's nothing that the equilibrium, the counterpart of the equilibrium, that's very important, of the second Newton's theorem of equilibrium. So, that equation remains to be proved. It says that divergence of sigma plus rho b equal rho a. Look, you see here the acceleration, you see here one force. So this stands from an additional force that comes out into the equilibrium due to the existence of stresses. Okay? That is what I will go back. So this is the, by the way, this is the compact notation, this is the initial notation for j equal 1 to 3. Okay? That is the compact. You look, if component of that would be component I of the derivative with respect to y of sigma yj. That's it. So this, the mut index is j, so this gives rise to j here. Okay? It's so important that I will write them even one by one equations. That's the fully explicit notation. I won't do that just in very specific cases, because this is the same way that Cauchy wrote them 200 years ago. That's an equation. I have the original, a copy of the original manuscript of Cauchy's, and 250 years ago, this was written like that already. That will recognize in elasticity theory, that is what is written in books. This is components x, y, and z of B, components x, y, and z of A, and these are the components of the stresses which are given here. Okay? So look at that. The difference of sigma x with respect to x, plus the derivative of tau yx with respect to y. Here is the derivative of tau xy with respect to x, sigma y, etc., etc., etc. This is the so-called Cauchy's equations of motion, which essentially is nothing else than force equal mass times acceleration. Although there are something that you won't recognize right now as forces, but they are sort of forces. Okay? Okay. Look, in sometimes the acceleration is zero or negligible. If it's zero, that means then sum of forces equal to zero. Okay? Then this is called equilibrium equations, which is the one that probably you examine in your structural analysis courses. The equation is like that. Divergence of sigma plus rho b, and these terms are zero or negligible. So it's those equations, but this term at the right-hand side being zero. That many times we'll do this hypothesis, because that means that accelerations maybe are not exactly zero, but they are very small, negligible, which happens in most of cases, what we call quasi-static cases, when the deformation is slow. When it's very fast, impact, earthquakes, and so on, then this term plays a fundamental role, fundamental and non-negligible. We'll talk about that in the future. What about the fundamental equation at the boundary? Well, if at the boundary we have known values of t star, which are known at the boundary, the forces which are acting on the boundary of the continuum media, of course the stresses have to fulfill that the traction vector in terms of the normal at the boundary, n times sigma, is equal to t. Okay? So this is something that we call boundary condition or equilibrium addition equation at the boundary. This word is not very fine, but it comes from tradition. In engineering courses, this is called the internal equilibrium equation, because it refers to points at the interior. All points at the interior have to fulfill this partial differential equation, partial in respect to space, and all points on the boundary have to fulfill that condition, n times sigma equal t star. I recall that b and t star are data that we are assumed to know. Sigma many times is the unknown, is what you want to know. Okay? So you have to solve these equations. At the end of the day, we will be able to do that. Look, there is another condition very important of the stress tensor that is not proved yet. It's going to be proven in chapter 5, which is the following. So far, I plot that in a non-symmetric way. Look, tau yx and tau xy here. It's not, I didn't say anything about symmetry. Symmetry cannot be proven from the theorem that we said before. Symmetry has to be proven by the Newton second part of the Newton second law. Equilibrium of momentum, so to speak. Okay? Equilibrium of torques. So, that I will take in advance, I will say you, sigma is a symmetric tensor. And so sigma equals sigma transpose, so sigma ij equals sigma gi. That means that from now on, instead of plotting here tau xy, tau yx, I will plot tau xy, because it's symmetric. Instead of plotting tau zx, I will plot tau z. And instead of plotting tau zi, I will plot tau zy. And also here, instead of plotting sigma 2, 1, I will plot sigma 1, 2, sigma 1, 3, sigma 2, 3. Okay. So, and now there are consequences on that. Due to the symmetry, then the divergence of sigma can be written also as sigma dot nabla. And then that is the way that we, in general, because sigma ij equals sigma gui, then that means that nabla sigma is equal to sigma nabla, and that is the way, alternative way to write the conditions. And also, n sigma, ni sigma ij can be written as sigma ij is sigma gi, so we can be written as sigma gi times ni, so this is the index counterpart of sigma times n. So n times sigma equals sigma times n. So we'll write always the boundary condition at the boundary as sigma times n or n times sigma equal t. And the equilibrium of the Cauchy's equation of motion in that way or in that way, in that way or either in that way. Okay? Due to symmetry, to be proven. Okay? The symmetry to be proven. Principal stresses and principal stress directions, very important concept. Look, I told you that the stress is one physical entity depending on points, which has components when I choose a certain basis. The components that then can be interpreted in that way as we have done. What happens if I change the system of coordinates to another system of orthogonal of Cartesian coordinates? Well, components will change. The stress will be the same. The tensor will be the same. Components will change. And then there is a theorem in algebra that says that whenever I have a second order tensor which is symmetric, there is a system of coordinates in which this tensor is diagonal. The component of this tensor is diagonal. What is our interpretation of that? Well, that means that there will be three planes in which this plot that will have in these three planes, there will be no tangential stresses. So there are three orthogonal planes in which the stress state is just a normal stress. Okay? How to find that? Well, that will be possible using some mathematical arguments. Let me say that these three directions, defining these three planes, are called the principal directions, and the three planes the principal planes. And the corresponding stresses are called sigma 1, sigma 2, sigma 3 in this case, and they are unique, and they are ordered. So sigma 1 is taken the largest, so the largest tensile, because our sign criterion is that positive is larger than negative. So the largest tensile of these three stresses is sigma 1, and the smaller tensile is sigma 3, and the intermediate is sigma 2. So we ordered them in this way. Look that in some, we'll talk about that, in some subjects like geotechnics, the order is inverse. We'll talk about that. But the continuum mechanics criterion is that the three stresses are ordered from large to smaller large is the tensile, the most tensile, smaller is the less tensile or the most compressive. Okay? And they are called sigma 1, sigma 2, sigma 3. And the corresponding directions are the principal directions or the principal planes. Okay? Did you know about the principal stress? Have you ever heard of that? Sure. Okay. Let's go for it. How do we compute that? Well, there is a way of computing what are these values, what are called eigenvalues, of a matrix which is originally given in the original system of coordinates, which are in terms of those. That is what is called the eigenvalue problem, can be written in that way. Maybe you can look at in Wikipedia if you are interested for that. In principle, we try to solve the problem sigma times b being a certain vector, equal lambda times b. Find what are the b's and the lambdas for which this equation has solution. Okay? And then, of course, we can just write that in that way, a matrix which is sigma minus lambda 1 times b equals 0. And for this equation have solutions different from 0, then the determinant of this has to be 0. And the determinant of this is, of course, sigma. What is sigma? Sigma is the stress tensor, which has some components, typically those components, right, that we know. Then I have to subtract lambda 1, so I have to put here minus lambda, minus lambda, minus lambda, and find the determinant is equal to 0. The determinant of that is in a scalar, okay? And a scalar which will depend on what? On lambda and on the coefficient sigma ij, okay? So this equation that is called the characteristic equation, which can be proven look like that. It's a third order polynomial in terms of lambda. Lambda cube minus a first coefficient which depends on the sigmas, on the coefficients of the matrix sigma, times lambda square minus a second coefficient that multiplies times lambda minus a third coefficient that equal to 0. This is a polynomial, and it can be proven that the three roots of this polynomial are always real. You know that not all polynomials have real roots. Roots are those values that makes a polynomial equal 0, okay? The intersection of the polynomial with the x, or 0, okay? So it can be proven that if sigma is symmetric, the three roots of that, which we, by the way, call lambda 1, lambda 2, lambda 3, which will be the three principal stresses, once ordered appropriately. The three roots would be real, so the positive or negative numbers, so physical meaningful. And look at this coefficient. Look at this coefficient. These coefficients are numbers. I just don't want to say, we'll go that later on, what is the expression of these numbers. But look, whatever these numbers are, if I change the original system of coordinates, the result, which is that these principal stresses, shouldn't change, right? Because that are physical stresses, which are the stresses in a specific directions of planes, right? So from reasoning on this equation, which is called the characteristic equation, says that these coefficients would have to provide the same solutions disregard what is the original system of coordinates. But when I change the system of coordinates, then the components of the stresses change, okay? So these coefficients, which are specific combinations of the components of the stress tensor, are invariants. That means that if instead of this system of coordinates, I take another system of coordinates, x double prime, y double prime, z double prime, the components would be sigma prime 1, 1, sigma prime 1, 2, sigma prime 1, 3. But then, if I want to compute those stresses, since the results are going to be the same, because there are physical values, stresses in certain planes, which are always the same, geometrically the same, that means that these coefficients in the new system, in the other different system of coordinates, should be the same. So when I say that the components of the stress tensor change when I change the basis, that's true, in general they change. But there are certain combinations of these components that will not change. That's very important for us, because they will be a scalar number, because these are scalars, that represent properties of the stress state that do not depend on the change of coordinates, on the system of coordinates. So sometimes, if you want to characterize in single scalars what is the stress state, then the best we can do is this I1, I2, I3, because the number that we get will be independent, not of the stress state, they will be dependent on the stress state, but will be independent on the system of coordinates that I use at this moment for this stress state. So they are called invariants, and they play an important role in solid mechanics. We'll know that. By the way, some invariants are sigma 1, sigma 2, sigma 3. So the principal stresses are invariant themselves. So disregard what is the original system of coordinates, the values, the solutions for this equation have to be always the same one. They are invariants. But also the coefficients of these equations are also invariants. Okay? Okay, so let me just talk about that, another concept. The mean stress and the mean pressures. I have the stress state, then the trace of this matrix, you know already, is the sum of the three components at the main principal diagonal, the main diagonal, right? Sigma 1, 1 plus sigma 2, 2 plus sigma 3, or in engineering notation, sigma x1 sigma x plus sigma y plus sigma z. So the trace is something that once divided by 3, so the mean value of the principal stress, of the elements at the principal diagonal is called the mean stress. As a scalar, it's called sigma m. Okay? Of course, if we change the sign to that, we obtain the mean pressure. The mean pressure, okay, is minus sigma m. It will be denoted by P and a bar on top. You will see that because pressure is a concept that admits many definitions. Mean pressure for us would be minus 1/3 of the trace of the tensor, which is the sum of the principal directions. Look, by the way, implicitly I'm assuming something that will tell you here that the trace of the tensor is one of these invariants here. Okay? I'll tell you. That means that the mean stress is also an invariant, okay? And the mean pressure is also an invariant. Something that doesn't depend on the system of coordinates which I am using to take the coordinates. By the way, in the case that I work in principal directions, then the principal strain in principal directions, the mean stress would be 1/3 of sigma 1, sigma 2, sigma 3. Okay? Otherwise would be sigma x, sigma y, sigma z divided by 3, or sigma 1, 1, sigma 2, 2, sigma 3 divided by e. Look, a spherical or hydrostatic state of stress is that stress in which the stress state in which the three principal stresses are the same. So when I go that, if I look to the principal directions, in general, the three principal stresses are different from each other. But it could happen in some cases that the three of them are equal. Then we said that the stress state I'm dealing with is a spherical, and also the name is hydrostatic or spherical stress state. Why the name hydrostatic? You know what hydrostatic means? Fluid at rest. And in fluid at rest, in all situations, in fluid at rest, this is what happens at the stress state. That is where the name comes hydrostatic. But also in some solids, in some situations, it could happen that at certain points, the stress state is hydrostatic. That meaning that the three principal stresses are equal to each other, so the tensor of the stresses has a number here, the same number here, and the same number here. That is what we call the spherical or hydrostatic state of stress. Okay? In general, not all the stress states are hydrostatic. But it's very interesting sometimes for us to inquire how close to a hydrostatic state is a non-hydrostatic stress state. And this brings to the splitting of the stress tensor in something which is any stress tensor can be split into the spherical stress state, which is a tensor, plus the deviatoric stress state. It's called sigma prime. Maybe you remember that from geotechnics? You remember the deviatoric stresses? Have you ever been taught about that? Well, we are recalling that. So, the stress state is not hydrostatic. But now, we define one stress state from this, which is hydrostatic. Which is the one which is the mean stress times 1. So it's a tensor, which is hydrostatic, so it's like that. But here, what has here? The mean stress, and a scalar, which is in turn the 1/3 of the trace of the original tensor. This is hydrostate, by definition, because this is a spherical state. Okay? And then what is sigma prime? Well, the difference of the original stress state minus the spherical counterpart of it. So this measures the deviation of the stress state from a spherical stress state. For instance, if the original stress state is spherical, how would be sigma prime? 0. And you can check it. Try with a spherical stress state, compute that, and see that the difference is 0. Okay? That is what is here. In the spherical are divided by that, and a certain number of proofs can be done by that. We'll go back to that when we talk about plasticity and so on, because this plays a fundamental role. We'll talk about that.